And good morning, ladies and gentlemen. We're back. And would you guys go ahead and take back out your changes lab diagram? Because what we're doing today, you're going to be doing on that lab.
Yep.
Today we have the mystery bulb challenge. And here is our new oblong bulb. It is not the same as our old oblong bulb.
It's the mysterious one.
It is the mysterious one. Okay, so we are gonna set this up the same way we did yesterday. We're gonna take some measurements, and what you guys are gonna do is you are gonna record those measurements on that picture that you drew yesterday.
Looks like that one up there.
Yeah,
right?
yeah. So just write down what our measurements are there, and then you can
Next to the
calculate.
ammeter, put the current.
Mm-hmm.
And next to the voltmeter, put the potential difference. And
Let go of me. Let go of me. All right, so here we go. So I'm gonna go ahead and just set this up here. Get on there.
okay, she's putting the ammeter in the circuit.
Yeah. And we're gonna just set it up the same way we did in the past. Okay, with this going over here. Now I can't forget to add this in here. Bloop.
So the ammeter is in the flow. The current will flow through the ammeter, through the bulb, and back here. The voltmeter is not in the flow. It's measuring across the bulb from one side to the other. It's measuring the potential difference.
Yeah, so you should already have this drawn out in your picture. Let's go ahead and get our calculations.
Let's get some data.
So first thing first.
Whoa, that's about 200 and we'll call it 270 milliamps.
270 milliamps?
Write that down. That's 0.270 amperes.
No, I'm gonna write that down too. 2.7, just so I have it. So this is the mystery bulb.
Yep.
Mystery bulb. Okay.
Mystery bulb.
Mystery
Now,
bulb.
we didn't get the voltage, so
No,
do
we
the
didn't.
voltmeter
Let's do it.
again.
Okay. And oops, sorry.
Huh. That's about 1 volt.
1 volt. Oh, okay. So 1 volt. All right. So, ladies and gentlemen, add that to your
diagram that
diagram
you've
there. And the things that you need to do are: we found the potential difference. We know we found the current. Calculate the resistance and the power on your changes lab down there.
And don't forget to show your work. Don't just write the answer down.
Mm-hmm. Show everything.
Read them in.
Okay. So, Boykin speaking from experience.
That's right.
Okay, so what does the bulb filament do during the first second after you connect the
Oh, you
circuit?
should
go
stop the thing and finish what we were asking you to do. Now let's go on to the next thing.
Okay, so
Take the voltmeter off.
Pay close attention to the bulb.
I'm gonna put it right here
Yeah, so you guys can see it. Okay, so
do that again.
Oh.
It doesn't come on like an LED, which is instantaneous. Notice?
Takes like a second. In fact, you know what I'm noticing is I have a good view over here. The ammeter moves
Well, we'll get to
first.
that second.
Yeah, and then
second.
oh, look at that, was super delayed. Dang. Okay, so there's a delay, right? It turns on
So-
slowly.
Yeah, it's not bright at the start. It slowly increases in brightness.
Okay, and then what does the ammeter needle do during the first second after you connect the circuit?
So while the light bulb is going from dark to bright, what's the needle doing? Whoa!
Oh, okay, so it kind of dink donk. It takes up and then it goes back like that. It
So
surges.
during that time when it's connected and current is flowing and the bulb hasn't lit up yet, then the current is high, and then as the bulb gets brighter, do it again, then the current diminishes. What the deuce?
What's going on here? Okay. What is going on? Oh, actually, let me go back to that last one. I wanted to say one more thing. Okay. So, I wanted to state that. So, if current is changing, then our resistance is also changing.
That's right, because the relationship between potential difference, current, and resistance is stated by Ohm's law. And if the current changes, the voltage was staying the same. We didn't have that, but the voltage stays the same. It's provided by the battery.
Yeah, there's an inverse relationship right there, right?
Yep. Yes,
If the current is going to increase, what's going to happen to the resistance?
Decrease.
If the current is going to decrease, that's because the resistance is increasing. Okay, so next idea. Too far. An ohmic resistor is ideal. So why does the current spike when you first close the circuit?
Okay, an ohmic resistor is ideal. What does that mean? That means the resistance is always the same. Okay, and
which means the current's always the same. And we saw there
it's
that
not
the current wasn't always
so
the
that's
same.
not an ideal resistor. It's a real world resistor.
And so why does the current spike when you first close the circuit?
I think that's going to be explained in the
our
next
next one right
slide.
Okay, resistance is proportional to temperature.
Remember, what that bulb is doing is converting electrical energy into heat and light. So it's cold at the start.
And it heats up, and as it heats up, we're going to be increasing temperature, we're going to be increasing resistance, and if our resistance is increasing, what's going to be happening to our current?
It's going to be lower.
It's going to be decreasing.
So that's what we're seeing. We're seeing the cold is lower resistance, and the needle jumps up. But as the bulb gets brighter, it gets hotter. That current goes down because the temperature is going up.
Yeah, this makes sense. Okay.
Now we're going to ignore that because
yeah, I forgot.
we're going to ignore that in our calculations because it makes life much too difficult. Life's difficult enough as it is. You may have noticed.
Okay, so I forgot to mention that. Yeah, we're going to keep that in the back of your mind. Okay, conventional current. We talked about this in 2 videos ago. Imagines that positive charges are flowing in a circuit from positive to negative.
So boys and girls, on your diagram, you've already got electron. Have you got electron flow
They
yet?
have electrons. Yeah,
Okay.
we wrote them in there.
So now put in the conventional current.
Okay. And why? Not negative. Sorry. And what's going on here? What are they saying? They're saying that it's not electrons that are flowing, but it's protons that are flowing.
They're positive charge carriers.
Positive charge carriers. Sorry, I think about it as
'Cause
protons.
what about the protons, Ms. Mo?
They don't move.
They're stuck in the nucleus.
Yeah, they don't move. They stay there. So positive charge carriers, which should be repelled and attracted, but
Yeah.
it's obviously not really what's going on. Okay, so if I asked you to put in your conventional current, put it in there, write it in there. This is what
When
it
you
would look
take
like.
a college physics class, you're going to have conventional current. There's just no
Yes.
two ways about it.
All right, so the homework that you guys have for today is going to be in the regular physics book. It's going to be page 511, page numbers 1 and 2, 515, 5, 8, and 9, and 517, number 11.
You guys can do this.
Go get it.